basically like we use numbers for maths. Egyptians used shapes and pictures. Take a look. For number 1, they used a strike or line. For number 2, they used 2 strikes or lines. For number 3, they used 3 strikes or lines. For number 4, they used 4 strikes or lines. 2 on top of each other. For number 5, they used 5 strikes or lines. 3 on top of 2. For number 6, they used 6 strikes or lines. 3 on top of 3. For number 7, they used 7 strikes or lines. 3 on top of 4. For number 8, they used 8 strikes or lines. 4 on top of 4. For number 9, they used 9 strikes or lines. 3 on top of 3 on top of 3. For number 10, they used half a circle or a curved line. For number 100, they used sort of like a whirl. For number 1000, they used a plant-like picture. For number 10,000, they used a finger with its fingernails. For number 100,000, they used a frog. For number 1,000,000, they used a man, in a kneeling position. These were the symbols used for counting in Egyptian maths. A simple example would be this. This would be 20,000, plus 1,000, plus 200, plus 30, plus 7, which will equal 21,237. Don't worry, it's pretty simple. The way for reading and writing numbers is quite simple. The higher number is always written in front of the lower number. And where there is more than one row of numbers, the reader should always start at the top left.
Thank you for that, Niven. That was a great introduction. Egyptians discovered the main parts of algebra. Now, Pinar, I heard you know some information. Please share with the class.
Well, I was reading a book last week and I did some research. This is what I found out.
Maths history in Egypt. In terms of using mathematics every day, the Egyptians were masters and had some cool techniques. Their mathematicians were so skilled that great Greek mathematicians such as Thales and Pythagoras learned techniques in Egypt. It all started with the Rhind papyrus. Here is a picture of it. This is a papyrus sheet. It seems to be a sort of guide to ancient Egyptian mathematics. It contains 87 math problems, including equations, volumes of cylinders and prisms, and areas of triangles, rectangles, circles and trapezoids, and fractions. The equations found on the Rhind papyrus. The equations include the equations we should know on area of prism, cylinder, triangle, rectangle and circle, and the volume of prism and cylinder. Algebra history in Egypt. Together with geometry, analysis and number theory, algebra is one of the main branches of pure mathematics. Ancient civilizations wrote out algebraic expressions using only normal abbreviations, but by medieval times, Islamic mathematicians were able to talk about powers of the unknown x, and work out the basic algebra of polynomials, without yet using modern symbolism.
The most important bit about Egyptian maths is history, so thank you for that, Pinar.
No problem at all.
Did you find anything, Kate?
Well, I found out that the eye of Horus was used for fractions. It's really quite interesting. Here, have a look. As you can see here, each part of the eye represents a different fraction. Using these fractions, the Egyptians were able to record prescriptions, land, and grain. The eye of Horus fraction system, based on the eye of Horus symbol, uses halves for each fraction.
The system is based on halves. Half of 1 equals 1/2, half of 1/2 equals 1/4, and so on until the smallest value of 1/64. By adding together the values of different sections, you can create different fractions.
Hope you enjoyed my information. Back to you, Zach.
Okay, last of all, Jess, what will you present to us today?
Well, I found some info about Egyptian pyramids. Firstly, I found out that Egyptian pyramids were built as burial places for kings and queens. They used slaves to build the pyramids. The construction of a pyramid involved ramps being placed around the pyramid, while blocks of stone were pulled up on sledges. The Egyptians used Pythagoras' theorem to calculate the hypotenuse of the triangle-shaped ramp. They worked out that if they used wooden sledges, the large stone blocks moved easily. Each pyramid had different levels. The Egyptians had to calculate how much stone they needed and what kind of shape it had to be in order to stay in place. If the Egyptians hadn't have structured them this way, we wouldn't be able to see them like we do today.
Thank you, Jess. The information was very interesting.
Okay, that's it guys for today. Let's go get some rest.
Here's a typical problem. If a field has an area of 55 units, and one side is 6 units longer than the other, how long is the shorter side? The Babylonian solution was to reconfigure the field as a square. Cut 3 units off the end, and move this round. Now, there's a 3x3 piece missing, so let's add this in. The area of the field has increased by 9 units. This makes the new area 64, so the size of the square are 8 units. The problem solver knows that they've added 3 to this side, so the original length must be 5. It may not look like it, but this is one of the first quadratic equations in history.
In modern mathematics, I would use the symbolic language of algebra to solve this problem. But the amazing feat of the Babylonians is that they were using these geometric games to find the value, without any recourse to symbols or formulas. The Babylonians were enjoying problem solving for its own sake. They were falling in love with mathematics.
The Babylonians' fascination with numbers soon found a place in their leisure time too. They were avid game players. The Babylonians and their descendants have been playing a version of backgammon for over 5,000 years.
So the Babylonians played board games, from very posh board games in royal tombs to little bits of board games found in schools, to board games scratched on the entrances of palaces, so that the guardsmen must have played at times when they were bored. And they used dice to move their counters round. People who played games were using numbers in their leisure time to try and outwit their opponent, doing mental arithmetic very fast. And so they were calculating in their leisure time without even thinking about it as being mathematical hard work.
Now's my chance.
I hadn't played backgammon for ages, but I reckon my maths would be good enough to give me a fighting chance.
Okay. So 6, and I need to move something, so...
But it wasn't as easy as I thought.
Okay.
Wow! What the hell is that?
Yeah, this is...
1, this is 2. Now you're in trouble.
So I can't move anything, can I? I can't move these anyway.
You cannot move these. You're gonna
I've just got to... Oh, gosh.
Exactly. There you go.
You seem to be...
3 and 4. So.
Just like the ancient Babylonians, my opponents were masters of tactical mathematics.
Yeah. Put it there.
Here you
All right, good game.
The Babylonians are recognized as one of the first cultures to use symmetrical mathematical shapes to make dice. But there is more heated debate about whether they might also have been the first to discover the secrets of another important shape, the right-angled triangle. We've already seen how the Egyptians used a 3-4-5 right-angled triangle. But what the Babylonians knew about this shape, and others like it, is much more sophisticated. This is the most famous and controversial ancient tablet we have. It's called Plimpton 322. Many mathematicians are convinced it shows the Babylonians could well have known the principle regarding right-angled triangles, that the square on the diagonal is the sum of the squares on the sides, and known it centuries before the Greeks claimed it.
This is a copy of the arguably most famous Babylonian tablet, which is Plimpton 322, and these numbers here reflect the width or height of a triangle, this being the diagonal. The other side would be over here, and the square of this column plus the square of the number in this column equals the square of the diagonal. They are arranged in an order of steadily decreasing angle on a very uniform basis, showing that somebody had a lot of understanding of how the numbers fit together.
Here were 15 perfect Pythagorean triangles, all of whose sides had whole number lengths. It's tempting to think that the Babylonians were the first custodians of Pythagoras' theorem, and it's a conclusion that generations of historians have been seduced by.
But there could be a much simpler explanation for the sets of three numbers which fulfill Pythagoras' theorem.
It's not a systematic explanation of Pythagorean triples. It's simply a mathematics teacher doing some quite complicated calculations, but in order to produce some very simple numbers in order to set his students problems about right-angled triangles. And in that sense, it's about Pythagorean triples only incidentally.
The most valuable clues to what they understood could lie elsewhere. This small school exercise tablet is nearly 4,000 years old and reveals just what the Babylonians did know about right-angled triangles. It uses the principle of Pythagoras' theorem to find the value of an astounding new number.
Drawn along the diagonal is a really very good approximation to the square root of 2. And so that shows us that it was known and used in school environments. Now, why is this important? It's because the square root of 2 is what we now call an irrational number. That is, if we write it out in decimals or even in sexagesimal places, it doesn't end. The numbers go on forever after the decimal point.
The implications of this calculation are far-reaching. Firstly, it means the Babylonians knew something of Pythagoras' theorem 1,000 years before Pythagoras. Secondly, the fact that they can calculate this number to an accuracy of 4 decimal places shows an amazing arithmetic facility, as well as a passion for mathematical detail.
The Babylonians' mathematical dexterity was astounding, and for nearly 2,000 years they spearheaded intellectual progress in the ancient world.